Hello, I'm Donald O'Hare. This is my recording for Lab 4. So I used the video they gave us for the mass on the end of the spring oscillating in 2 dimensions in the tracker model, and we already knew that the mass was 0.402 kilograms, the spring constant was 6.83 newtons per meter, and the relaxed length of the string was 0.123 meters. So I used the tracker video to make the initial condition for the glow script, and then I compared the tracker data to the coded model, and the two actually matched up pretty well, but there was a little mismatching. So the motion of the spring was over 9.5 seconds. The mass was acted on by gravity, the spring force, and air resistance, and any movement in the z-axis was ignored. So the origin was set at the point where the end of the spring is fixed to the wall. The system was the spring, mass, and air's gravity, and in real life, the air was the surroundings, and I guess the friction in the spring as well. And both dimensions of movement, x and y, exhibited harmonic motion, as you can see in the picture there. So in GlowScript, the velocity and position update formulas over short periods of time were used to iteratively predict the velocity and motion based on the net force. Initial position was set at negative 0.132 meters, negative 0.6950 meters, and the initial velocity was 0.816, negative 0.211 meters per second. The net force was F spring and F grav, and for the purposes of our energy calculations, we assumed that the spring was perfect and that air resistance was negligible, which of course isn't the case in real life. So taking that into account, in the simulation, the spring, mass, and gravity were the system and there were no surroundings, which let's just say delta E equals 0. And so the change in potential energies of the spring and gravity along with the change in kinetic energy made the total delta E, which were also calculated iteratively for this. So the X position was modeled pretty faithfully, and the Y position, as you can see, was also pretty accurate, but just displaced slightly. I'm not 100% sure what caused this. It could have just been setting it up in tracker wrong because, as you can see, it's off by only a little bit, but it's just the orientation of like where it begins. So it also could have to do with, as you mentioned before, the imperfections, the imperfect spring and air resistance, movement in the z-axis, and you can also see that the energies would graph to total delta E of 0 consistently, which is accurate with what we expected from our calculations. So it does show that the energy principle is maintained in the simulation because we didn't have those dissipative forces of internal friction and air resistance. And the period of oscillation based on the tracker data in the x-axis was 1.615 seconds, and the period of oscillation in the y-axis was 1.52 seconds. And these are both relatively close to each other, and any differences are likely due to just tracker being an imperfect way of getting the data. You know, it's only 30 frames per second or so, so that we didn't get the exact peaks of each one, and also they started like I took the data points starting at different times for the period of oscillation, so friction and air resistance likely also caused a little bit of a mismatch there but they should be exactly the same in a perfect world because the period of oscillation only has to do with the mass and the spring constant, which would remain constant for the x and y. So overall, it shows us the energy principle in action and how that it doesn't always work perfectly in real life because we're always going to have something like air resistance or friction, at least on Earth, to dissipate energy. But it does let us get pretty close. And then again, it's another example of using these conditions to model motion, and we actually did it pretty well this time.